Okay, welcome to the Thursday morning session, at least in Korea. We'll have three talks. The first speaker is Nathan Secrest. Nathan, can you start?
Yes, thank you. Okay, hi everyone, or hi again everyone. I've been kind of in and out of this meeting throughout the week. It's about 8 p.m. DC time, so I've been missing the afternoon sessions, unfortunately, but nonetheless, it's been a very pleasant and enjoyable conference, and I thank the organizers for inviting me to come and talk about this recent paper that myself and my colleagues published called A Test of the Cosmological Principle of Quasars.
Can you switch it to full screen mode?
It didn't work earlier, so is this okay?
Yeah.
Okay, so there's two caveats I just wanted to point out really quickly. I get the impression that there's a lot of sort of consternation and strong opinions about the cosmological principle and about the various tests that have been made of it. I'll just say that this paper was the first paper that I've ever written or even participated on in cosmology. So I'm not a cosmologist by background. And you'll probably see that throughout the talk. It's a very non-technical talk. And if I make any sort of silly statements, don't hesitate to call me out on it. But I don't really have any feelings about the cosmological principle one way or the other. I just think that the results that we're getting is very interesting and difficult to explain, especially considering that it seems to confirm results independently hinted at in previous work. So a kind of non-cosmologist understanding of lambda CDM looks like the sort of classic press release picture of the CMB from Planck. Most extragalactic astronomers sort of have this general idea that there's these anisotropies in the CMB, and you can fit this with spherical harmonic decomposition, and then from that you get your main the parameters of your model. These anisotropies are sort of 1 part in 100,000, but nonetheless the sensitivity of Planck and these designated emissions has allowed us to get exquisite precision, and that is a key thing to point out, that it is precision. But nonetheless, the main sort of takeaway is that co-moving observers see the same universe everywhere in lambda CDM and in cosmologies like lambda CDM. So this is referred to as the cosmological principle. But in fact, the microwave universe doesn't actually look like that nice picture. It looks a little bit more like this. You've got a lot of galactic emission that needs to be masked out. And then you've got this dipolar pattern on the sky. And the sort of general idea is that this dipolar pattern, or perhaps more natural or simple idea, is that the dipolar pattern is because of our own peculiar motion in our little neck of the woods. And when you correct for this motion, this dipolar pattern in the CMB, you get a net velocity of about 370 kilometers per second. So this is used to sort of take out the so-called kinematic dipole from the CMB, do some fancy masking and inpainting, and then you get this nice CMB map. But all these different local factors, the Earth's motion around the sun around the galaxy, so on and so forth, is what is thought to lead to this kinematic dipole. A key takeaway is that this dipole should be the same, because it's kinematic in nature, for all cosmological sort of test particles like galaxies and quasars that move, for lack of a better word, in the Hubble flow. But this is only true if the cosmological principle is correct. And so there's this nice blurb that Sabir sent me from one of his talks from Steven Weinberg that points out that the cosmological principle is in fact a simplifying assumption, because otherwise there'd be too many degrees of freedom, too many model parameters to fit, and it's been a very effective assumption thus far. But nonetheless, if we find data that doesn't fit that assumption, this is very interesting and very important. So one way to approach this is to look for CMB independent data or measures of the kinematic dipole. This is really of critical importance for an independent test. And so the way we do this is by using the classic formula from Ellison Baldwin. Essentially, all you need for this is you need some preferably very large scale flux limited catalog, some estimate of the spectral index of your sources within whatever passband you're using. And then you need essentially to make a histogram of those flux densities in order to get the integral source count per unit solid angle. So you plug all this into Ellison Baldwin, and that gives you the predicted dipole amplitude for a given velocity, in this case, 370 kilometers per second. So if you didn't have a velocity with respect to the large scale sort of standard of rest with the rest frame of the CMB, then if the cosmological principle is correct, you would expect galaxies and quasars to kind of be more or less isotropically distributed throughout the sky with no real preference from one direction or the other. But with the kinematic dipole, you get this, relativistic aberration and Doppler boosting, and that causes one portion of the sky to be overrepresented and the opposite to be underrepresented. Of course, this is very greatly exaggerated. And again, I apologize if this is obviously very simple for this crowd, but this is just kind of going into my own understanding of what the problem is. But real catalogs don't, of course, look like this. They're decidedly messier. So this is a Hilpix map of NVSS, and it just shows some of the issues that face real catalogs. You get galactic contaminants along the plane, supernova bubbles, things like that. You get changes in sensitivity depending on your declination. You get incomplete sky coverage, and all of these things can conspire to give you to hide the intrinsic signal from your data. So usually the way we do this is we do masking and we make flux cuts, and at the end of it you should sort of see a shot noise limited sky, and this is what has been done in the past to try to eke out this dipole signal. And so these are some results from past work using mainly the NVSS. I apologize if there's anything missing. I kind of made this table in a little bit of a hurry, but it just shows the measured dipole amplitude as well as the significance of the measurement. But the takeaway here is that the dipole in NVSS is consistently about 2 to 3 times larger than the expectation for the NVSS, which given its frequency is about 0.0046. The significance of these results has been limited so far. Once you make the masking and flux cuts that are required, you generally end up with a catalog that has something like 200,000 to 300,000 sources. So you are sort of shot noise limited. Nonetheless, the interesting sort of wrinkle in that result is that the direction of the dipole, despite being 2 to 3 times larger than expected, is pretty close to the CMB's direction. And there's a recent result by Seward et al. That used the measured dipole from other radio catalogs and at other frequencies to argue that the dipole, the anomalous dipole, may actually show a frequency dependence. So is this something real, or are there remaining systematics? Well, there are a lot of systematics in any catalog. And in the radio, one of the main sources of systematics is, of course, our galaxy. So this is a beautiful map from the Venerable Haslam 1982 480 megahertz survey. So the emission you're seeing is predominantly synchrotron. And so the takeaway here is that you get a lot of systematics that are due to bright sources, due to brighter background, that can affect these results, and definitely do show frequency dependence. So what do we need? What we need is a systematically independent quasar catalog. We need something that has no shared sky scanning pattern, no shared instrumental design, no shared foreground systematics, a minimum, preferably a minimum of shared sources, and of course, we all like better statistical power. So this is where the Wide Field Infrared Survey Explorer, or WISE, comes in. So this was a full sky mid-infrared survey between 3.4 and 22 microns. It's been in orbit for about 12 years now. And the majority of its data is now just in the first two bands because the cryogen ran out. Nonetheless, those first two bands are the most sensitive to what we're interested in, which are active galactic nuclei. So this is a plot from Nedderite's 2010 paper on WISE. And it shows qualitatively, although this is surprisingly accurate, the different locations of astrophysical objects in WISE color space. And the takeaway here is that a simple one color cut, W1 minus W2, so 3.4 minus 4.6 microns, cleanly separates AGNs from stars and most galaxies. So this has been done before. I published a paper about 6 years ago now on a catalog of quasars that was designed really to be used by Gaia in validating and tying its reference frame. Roberto Yosef published a catalog later of AGNs using a different color cut. This was designed more for people who actually work on AGNs, so it's a little bit more complete. But nonetheless, the work that's been done so far shows that this is a proven reliable technique, that you can use color cuts, mid-infrared color cuts alone without even having redshift information. But the selection criterion depends on what you need. So what do we need? We need a uniform, homogeneous, clean, and flux-limited quasar catalog. And so this turned out not to be really very easy to do with the old all-WISE catalog. But fortunately, the ERSA team released CatWise 2020, which includes about 6 years of additional data from the WISE reactivation or NEO-WISE mission. And that greatly improved the uniformity of WISE coverage across the sky, as well as greatly improving the depth of the survey, especially in the W2 band, which is the most sensitive to AGN emission. So we produced a raw AGN catalog using the Stern 2012 color cut. This was the W1 minus W2 of 0.8 mag. And this was what our raw catalog looked like. And as I mentioned earlier, all catalogs have their systematics. So you can see there's some extended contaminants, there's a varying depth, and there's also source confusion. So WISE has an effective resolution of about 6 to 8 arc seconds. So once you get near the galactic plane and also nearby galaxies, you start to see a depressing effect on the number of sources. So for the varying depth, fortunately, the CatWise catalog has a very well understood completeness limit. And so the solution was quite simple. We just cut on a W1 mag of 16.4. This was the result. And you can see there's still some remaining systematics, but the overall uniformity outside the galactic plane is quite good. So for the objects that, the contaminants that remained, we made a mask that included the Large Magellanic Clouds, galaxies from the 2MASS extended source catalog, and a few bright stars. And of course, we included the galactic plane, and this was the result. We're looking a lot better. But looking a lot better is not the same as actually being better. So we did some more statistical tests, and we found that there's a systematic with galactic latitude out to surprisingly high galactic latitudes. We ended up having to make a cut of plus or minus 30 degrees. We also found that for a given flux cut, there's a reduction in the source density as a function of ecliptic latitude. This is ironically because the ecliptic poles actually have greater depth with WISE, which means that the fainter sources picked up in these deeper coads have the effect of causing confusion, which can actually depress sort of statistical or random way the recording of brighter objects. But fortunately, this result is quite linear, and we were able to correct for it. So here's our final catalog. Looks a little bit different from the previous plots just because this is what's actually in the paper. But what we came up with was 1.36 million AGNs. And just as a kind of sanity check, we decided to do something that you don't see in a lot of papers, which is namely that we smoothed the map to see if whatever dipole signal we find or don't find actually comports with what we see. And in fact, we do see it. It's quite clear. So this is a map of the of our final catalog smoothed using a running average. I think it was a 1 steradian smooth. We didn't run any sort of Gaussian filter or anything like that. It's a simple average. But the point is that it reveals a very clear dipole signal. So for the estimator, we ended up using a least squared quadratic estimator as a new estimator that Sebastian von Hassiger came up with that improves on previous quadratic estimators, and moreover does not suffer from the biases that the so-called linear estimator suffers from. So the eagle-eyed amongst you may have noticed that when we first put out the paper prior to publication on arXiv, the significance of our result was considerably lower. And that's because we had originally used the linear estimator, which caused some issues with bias that we didn't fully appreciate. So to circumvent this issue, we ended up going with this quadratic estimator, which we proved not to be biased, and it greatly improved our significance. So the key takeaway is that this estimator recovers input dipoles with arbitrary asymmetric masks and is not biased. So our dipole amplitude is shown here. It's 2.2 times larger than expected, which is in line with the radio results. Also in line with the radio results, although not plotted here exactly, is that the direction is somewhat similar to the CMB dipole direction. So how did we estimate the significance? We produced 10 million random skies. And for each iteration, we produced a catalog of exactly the same size as our own, or the original catalog, sampling randomly from the empirical flux density and spectral indices distributions. We applied the same masks, and then we applied relativistic aberration and Doppler boosting. We only kept, after applying this aberration and Doppler boosting, we only kept sources with modulated fluxes that met our original flux cut. And so this was our result. We found that only 5 in 10 million instances exceeded the found dipole. So this is a p-value, obviously, of 5 times 10 to the minus 7, which if you convert that to a normal distribution, although the posterior distribution is not quite exactly normal, but it's 4.9 sigma for a one-sided distribution. And you can see that very clearly that the found dipole in catwise is completely inconsistent with the expectation from the CMB. On the right, this shows the 95% confidence interval, or 95%, I should say, realization interval for the recovered direction of the input CMB dipoles. So the direction of the found dipole is sort of just at that limit. It's sort of at the 95% level. So again, this independently confirms previous radio findings, although at a much higher significance level. Okay, so this is the local universe, and it's one of my favorite maps of the sky. It's from 2MASS in supergalactic coordinates, and it shows the local universe out to about a redshift of 0.1. And the catch here with all these results is, of course, we have to estimate the contribution from the clustering dipole, the random dipole in the sky that's just due to local clustering. So in order to do this, we took redshifts from eBOS that were along the deep stripe 82 region. We found that 99% of quasars that were not heavily obscured, at least, had spectra, and 99% of those also have redshifts, I should say, greater than 0.1. So sort of outside of the redshift range in which the clustering dipole is a significant issue. So plugging in our redshift distribution into the prediction from lambda CDM, and I'm not going to go over the mathematics because I don't personally understand it, but my colleagues do, we got our clustering dipole, and we found it to be 65 times smaller than our found dipole. So the clustering component of the quasar dipole is negligible, in other words. So something to remember here. The previous results were in the radio, predominantly with NVSS, which was taken with a very large array in New Mexico. This result comes from WISE, which is an orbiting mid-infrared telescope. So these are completely independent surveys. And as a bonus, I did this a little bit later, but if you match the cat-wise quasars to the NVSS, you find that only about 1 to 4% sources, depending on exactly on how you do the match, only about 1 to 4% of the sources are shared between the two catalogs. So as a bonus, the mid-infrared quasars and the radio galaxies actually have minimal overlap. So not only is the survey strategy and all the instrumental effects independent, but the sources themselves are almost entirely independent. So this is a really reassuring result that indicates that what we're seeing is astrophysical. So that's it. This is my presentation. So just to summarize, using data from WISE, we've created the largest cosmology grade sample of quasars to date. This sample confirms the anomalously large matter dipole, if we assume the quasars trace matter, suggested in previous radio studies at 4.9 sigma. Again, WISE is systematically independent from radio catalogs, which strongly supports the reality of this anomalous dipole. And this result is therefore in conflict with the cosmological principle, which is one of the foundational assumptions of lambda CDM and cosmologies like it. So if you want to check our results, please do. I would love to find, if we are doing something wrong, I'd love to see it, but I'm beginning to doubt it at this point. All of our code and data is available at this link, and our paper is open access, so it should be available to everyone freely. Thank you.
Okay, thank you very much. So as you predicted, you finished quite earlier, so we can take some questions. Now, let's see. There is a Yoin, do you?
Yeah, I have one in the chat. He can just, Nathan, basically on Tuesday, there was discussion about a tomographic dipole, right? So we're looking at SKA, right? But we already seem to have the radio galaxies are a bit closer than the quasars. Have you got any comment?
Yeah.
Like, so basically what Roy was saying on Tuesday was basically he was reinforcing the expectation that as we go out, you know, as we look at the matter dipole and go out in redshift, eventually we should recover the CMB result. But already, you know, do you believe that's going to happen?
I mean, I suspect that if we're still seeing a significant clustering dipole effect at a Z of 1, we're already pretty hard in tension with lambda CDM as we know it. But I do know that radio galaxies do tend to be a little bit closer in redshifts than mid-infrared selected quasars. That might, you know, there might be some additional clustering dipole for catalogs, for example, like TGSS, which seems to show an especially anomalous dipole. To my knowledge, nobody has done a redshift survey of TGSS, although TGSS has a lot of issues systematically. It's a very noisy map, and it has problems with flux calibration. So I don't doubt that there may be some both instrumental and potentially cosmological systematics in the radio catalogs. I'm a little bit more skeptical that it's present in a significant way in the mid-infrared catalog.
Thanks.
Any other question? So you showed in almost at the end, showed the redshift distribution, what is this distribution for? This is your sample or? Yes,
so this is, we chose a portion of the sky that had the deepest spectroscopic coverage possible. So we chose the EBOS footprint, and specifically the footprint along stripe 82X, which also has coverage with the dark energy survey. Because one of the things we wanted to understand is the nature of any objects that don't have spectra. So the dark energy survey is very deep in the optical. I think it goes to 24th magnitude. So we first matched on the dark energy survey, and we found objects that mid-infrared selected regions that don't have EBOS spectra have very red optical minus mid-infrared colors, which is a known proxy for Compton thick and heavily obscured AGNs. and that's an orientation effect to first order. So in other words, we don't expect there to be a systematic difference in redshift. So that's what we did, and then we used the redshift distribution for the matched objects as a proxy for the whole.
So there are hands up in case you haven't.
Douglas?
Yeah. Right. Forgive me for being skeptical, Nathan, but I'm always skeptical. If
Please
you
do.
go back, I mean, I did read your paper in detail because I thought it was interesting. If you go back to the number count plot, the red and blue thing,
Forward or back?
but back, yeah. Well, I think back. The one with the main result. So I mean, you show this and say there's a clear dipole. So I don't see a clear dipole. I see a thing with the large dipole component, but I see other stuff in here that looks about as strong as the dipole component. And the other stuff is presumably not the dipole, and therefore caused by something to do with the survey or the analysis or the way you did the extinction or whatever. So this does not reassure me that you've detected just a dipole.
Yeah, so we didn't find a very notable correlation with any preferred survey directions or foregrounds, like, for example, the extinction map in some of these overdense or underdense regions. If I recall correctly, Sebastian did attempt to fit fit a quadrupole and I think also an octopole to the map, but the significance of the fits were quite low. So my understanding, and perhaps Sebastian's on here is in the conference somewhere, but my understanding is that once you subtract out the dipole component, the variations that remain are somewhat random.
Well, it doesn't look like that to me. I mean, the reddest thing is not opposite the bluest thing. And there's kind of structure in here. So I mean, this does not look to me like a dipole. So then the follow-on question would be how good is the best fit to a dipole?
How good is the best fit? That would be a question. Right? Yeah, I'd have to ask Sebastian for a little bit more about his fits. I know that we did, we validated input dipoles and we validated that our method was not biased in any way, but beyond that, I couldn't answer any more technical questions about it.
Okay, thanks.
Okay, thanks. There's one more question.
Yep, it's me.
Yeah, okay, Darwin, yeah.
I can stay invisible. No way to start video. It's fine. Nathan, very nice talk. Very clear. Thanks very much. I just have a technical comment, but you have your estimator that's quadratic. Chris Hirata in 2009 derived estimator that's by some measures optimal. It's unbiased for sure. It's very easy to apply, and also it gives you the Fisher matrix, so it gives you the error bars right away. So it gives you significance. You don't have to run Monte Carlos. And that's what we used in the Gibelliu paper, what I used in shortly thereafter. So I haven't looked at this in a long time, but that seems like, I don't know which estimator is the best, but that's a very nice one. So it might be worth, I don't know if you've done to compare your results with your estimator with that estimator for which you don't need Monte Carlos, and just see how significance compares.
Yeah, so I'll just, a little just clarification is that the Monte Carlo simulations that we did was not to try to estimate the error of the found dipole itself. It was purely a frequentist analysis to estimate the significance of the found dipole given the null hypothesis, namely that the kinematic dipole.
Oh, I understand. Okay, understood. Yeah, I misunderstood that part. Okay, thank you.
There may be some sort of covariance matrix or something that comes out of that fit. I don't know. It wasn't something.
But it's still worth. So right. So that part I misunderstood. But it's still worth comparing the estimator itself just to see if you get the same.
Yeah, we did compare the estimator to multiple other estimators as a sanity check. So
Nathan, what was the significance of the linear estimator? Just I know it's biased.
It was
just to get a feel.
I think it was on the order of 3.9 sigma or something. And that was with the unaccounted for bias.
Okay.
So, and namely that the bias, that if the linear estimator produced more of a bias for a smaller input dipole. So when you produce a bunch of null skies with a CMB dipole, which is smaller, your posterior distribution will skew high, and that lowers your significance. So that lower significance from the original manuscript that we submitted to Astro PH prior to prior to peer review was with that bias, which we hadn't fully accounted for or hadn't quite comprehended. So that's why we decided to use this estimator.
Okay, so getting back to Dragon's point, I guess we probably will find this is over 3 sigma, right? Dragon.
Oh yeah, yeah. I mean, it's there's no doubt it's over 3 sigma. In my mind, there's no doubt it's over 4 sigma. And because the sample is independent, almost entirely independent of the radio sample, it wouldn't take. I very strongly suspect that a joint analysis would push it over 5 sigma quite easily.
Okay, so since we are running out of time, let's move on. We have a few more questions, but we can postpone this after the all the other talks. So thank Nathan, and next speaker is Douglas Scott, and he'll be talking about dipoles. Okay, go ahead. You can see it.
Sorry, I was muted. You can see it? I had intended to say some things about the dipole, but many people have already spoken a lot about the dipole, so I've changed a bit what I was going to say. So my new plan is to give you bits and pieces of things relevant to the dipole and go through it relatively fast in the hope that for everybody there's at least a tidbit in there that you haven't heard before. But hopefully there's of some interest to everybody in here, but much of it you might have heard before. So we have these beautiful maps of the CMB sky, which you can decompose into this power spectrum. And this is the thing from the review article that I wrote with George Smoot and updated just recently. If you think about the dipole, you have to shrink this way down so that you can't even hardly see it because the dipole is way up here. So the dipole is genuinely big compared to all the other multipoles. So it's clearly there's something different going on there. So let's, instead of talking about the usual CMB precision and all the sigma and how it's only fit by 6 parameters and so on, let's just focus on the dipole here. Why is the dipole so big? So the standard explanation is because your Lorentz boosting giving you dipole modulation of the monopole. And because the monopole is so big and V over C is of order 10 to the minus 3, you get a dipole which is millikelvin rather than Kelvin, and all the other anisotropies are 10 microkelvin or so. So it's 100 times bigger than all the other anisotropies. So it's just because the monopole is big and beta is 10 to the minus 3. So remember, the sky is dominated by this monopole, and that's the thing whose modulation gives you the large dipole. And then you have to take off the monopole and the dipole in order to see all the usual anisotropies. That monopole has a very close to black body spectrum, as George Smoot already discussed a little bit and was involved in some of the measurements and so on. And it's the best black body there is. You can't get a black body to calibrate this black body that's better than this black body. So that's one of the cornerstones of the hot Big Bang model, i.e. the universe used to be hot and dense and in thermal equilibrium. You can extract a few numbers from the monopole. So the temperature is known to the 4th digit. You can work out the number of photons per unit volume. You can work out the energy per unit volume in various units. You can work out where the spectrum peaks to several digits and so on. You can put it in everyday units like Celsius, and for my American friends, this is the value of the CMB temperature in Fahrenheit, which probably you haven't seen before. And if you want to do it in dimensionless units, if you express it in terms of the rest mass of the electron, it turns out to be about 2 to the minus 31, or the rest mass of the proton, it's about e to the minus 39. So those are easy numbers to remember. There are, of course, other backgrounds, and this is a compilation of background radiation across the full electromagnetic spectrum, put together mostly by my grad student Riley Hill, and put out in a paper called The Spectrum of the Universe, in which we have this very nice plot where the line is thin, where the data are have very small error bars, and the line is fuzzy looking where the error bars are larger. You should have a dipole for all of these backgrounds, by the way, because they're all modulated by 10 to the minus 3. So the monopole has this precise measurement. One of the things that's interesting to think about for the monopole is, because we live in a universe which has of order 10 to the minus 5 inhomogeneities on all scales, including the largest scales, then we expect delta t over t to be of order that much on large scales, and we could live in a 3 sigma fluctuation or something. So if you think about that, what that means from the error bar, we're only about a factor of 10 away from cosmic variance on T naught. So in other words, we'll reach a point where we know what T naught is in our Hubble patch, but it stopped telling us about what T naught is for the average universe, assuming that that means something. The monopole, of course, is coordinate dependent. So we live in a potential, which is in another potential, and so on. So the true CMB isn't what we measure, but the differences of order are of order v squared or c squared, or the potential. So it's in, the 7th digit or something for the Earth's potential, the solar system potential. But it helps understand that the monopole is coordinate dependent. So it depends on how you slice the coordinates. And the dipole similarly is coordinate dependent. Just you can talk about fluctuations in the dipole, but you really realize that it depends on your coordinates, or it's gauge dependent. But nevertheless, you can calculate the transfer function for the perturbations in the monopole. And we did this, I think, for the first time in this paper in 2008 with Jim Zibin, which I encourage you to read if you're interested in more details. So there is a sense in which you can talk about the variance of the monopole that observers of Hubble patches would see, even although within our Hubble patch, we can only observe what the CMB temperature is on our last scattering surface. Just to finish talking about the monopole, what's the study of the monopole called? And it's obviously called this. And then to move on to the dipole, the study of the dipole is obviously this. Okay, but I did say I was going to talk about the dipole, and I've spent more than 5 minutes talking about the monopole already. So let me move on to dipole. This is the dipole from Kobe, which George Smoot showed. There was no real dipole from either WMAP or the early Planck releases. And that's because the dipole is wrapped up in calibration, so you sort of remove it. So you can get a Planck map with the dipole, but it's because it's been put back in, which seems a bit circular. However, the recent reanalysis of the Planck data, called Public Release 4, or sometimes called NPIPE, didn't remove the dipole, so kept the dipole in the map. So you can show Planck maps with the dipole in for the first time as of a couple of years ago only. Remember, the dipole also is gauge dependent or coordinate dependent. In other words, it depends what frame you're in, what dipole you measure. The most obvious thing for us to do as beings made of matter is to choose the co-moving matter field as our rest frame. And then in principle, the co-moving, the rest frame of the CMB radiation could be different. And the dipole has a large contribution from small scales. So in other words, it's the local pools of things in our local neighborhood that cause the large dipole that we see. there's no intrinsic dipole for adiabatic perturbation since the matter frame equals the CMB frame. Let me say more about that in a second. So we normally think about the dipole as being dominated by this extrinsic motion. In principle, there's a perturbation on our Hubble, from our Hubble patch, there's a perturbation on our last scattering surface, which is the L equals 1 dipole, which is of order 10 to the minus 5. So whether that is even in principle observable kind of doesn't matter because it's so small that we'll never observe it anyway. And I have had arguments with people kind of after a conference about whether it's observable or not. So we could do that in the discussion if you like. But in principle, you could tell the real motion from other effects such as aberration. And I had a discussion with Miguel yesterday. Or you could add up all the accelerations from all the lumps of matter nearby. And if you don't get the CMB dipole, then there's somehow an intrinsic dipole. So there's been arguments in the literature for decades actually about the idea of an intrinsic dipole. And I think you can make these arguments as complicated as you want, but I think the simplest way of thinking about this is if you have adiabatic perturbation, so you perturb matter and radiation the same way, then there's only one degree of freedom. And then what that basically means is that if you see a dipole, you're moving relative to the CMB. If you're moving relative to the CMB, you see a dipole. And the only real way to have an intrinsic dipole is to have non-adiabatic perturbations. So basically isocurvature perturbations. So you have some kind of tilted universe where there's literally a slope across the Hubble patch, where there's more photons on one side than the other, but it's not connected to an adiabatic perturbation. And of course, the perturbations look adiabatic on all scales, but maybe they're different on the very, very largest scales. But that would be, that would be not what you'd expect based on your expectation from all the other scales, but it's certainly possible and worth continuing to test. I wanted to just remind people, although it was mentioned in a talk yesterday, that Planck did this kinetic Sunyaev-Zeldovich effect measurement, which is not very prominent because it's buried in an intermediate paper 13. So the kinetic Sunyaev-Zeldovich effect from individual clusters has an uncertainty which is of order 1 sigma or less. But there's a lot of clusters that you can average over the sky. So you can work out that on sort of gigaparsec scales, you can't have a bulk flow. In other words, there's no dipole in the cluster kinetic Sunyaev-Zeldovich pattern up to sort of 250 kilometers a second or something at 95% confidence. So I would say it's fairly clear that the matter and CMB frames are basically the same. But the question is, are they exactly the same? Is it a redshift dependent effect and so on? So it's definitely worth studying. Let me say a little about the actual dipole that Planck measured. Of course, it's completely wrapped up in the calibration. The orbital dipole, the Earth going around the sun, which is known to like 10 digits in the right units, can be used as an absolute calibration. And then you can measure the solar dipole. And that, with various measurements over the years, Kobe, WMAP, and then Planck, culminating in Planck 2018. And there's a couple of more recent reanalyses of Planck since then, but they basically get the same answer with slightly smaller claimed error bars. The direction is known to certainly 30 arc seconds, probably a bit smaller than that. But the uncertainties are systematics dominated and not statistically dominated. The 2015 dipole was very conveniently 0.12345% of the speed of light. But sadly, that was the central value. Sadly, when it was measured again in 2018, it had moved a little bit from that, so it's no longer the case, but it's still 123. The direction, I think George Smoot in his talk talked about how it was in Leo. It's actually moved slightly since the earlier detections. So it's actually in the constellation Crater. And you might be saying, what's the constellation Crater? I've never heard of that. What's that constellation famous for? Well, it turns out it's the direction that we're moving towards. And that's about all it's famous for, because it's a little relatively unknown constellation. And it turns out it's really quite close to the border of Crater. So I spent a while trying to find out how you actually figure out what constellation you're in. And you need to look up, these were all defined according to RA and DEC lines in 1890 something, but there's been precession since then. So it's actually a little tricky to figure out, but I'm 99% certain that it's here right near the edge of crater. So that is, you know, the special direction in the universe that we're moving in. But of course, it's frame dependent. So there's all these other motions. And in particular, the sun going around the Milky Way turns out to be in almost exactly the opposite direction, which is another one of these coincidences that the universe gives us. So although it's 300 and something kilometers a second, once you correct for the sun going around the galaxy, did I say solar system there? Galaxy. It's about 600 kilometers a second. So that's sort of the number that cosmologists should most care about, because that's the speed with which the local group, if you like, is going through the sea of CMB photons. The CMB dipole also changes. I don't know how much you can see this movie, which is probably makes you sick if you watch it too much. But as the you know, to really figure out something to do with CMB foregrounds, what you should do is wait till the foregrounds change. And certainly the CMB dipole will change as we move around the galaxy. And that would be interesting to do, but it's going to take a long time, and then not in your lifetime will we be able to do that. We have, on the other hand, seen quasar proper motions that are affected by the changing speed around the Milky Way. So in other words, the acceleration of that is actually measured. And it's a little surprising. Most cosmologists have not heard of that, but it's not a particularly disputed measurement. It's a hard measurement to make, but it has been made. So the monopole is this 2.7255 Kelvin. CMB less scattering defines a rest frame. It's the rest frame in which there's no observable dipole, 370 kilometers a second in the direction of crater. And the local group's moving at about 620 kilometers a second relative to the CMB. There are other effects of boosting. So assuming that the dipole is just caused by this Doppler boosting effect, then you should certainly dipole modulate the monopole, and that's the dipole, but you should dipole modulate all the other multiples, and that's what Miguel calls the Doppler effect, I think. And that has a wide distortion spectrum. And my student Raylene Sullivan led the Planck paper, which was the second last paper by the Planck collaboration, in which we showed that we could detect that. There's also aberration. There's an increase in the monopole by beta squared over 6, and there's a generation of an order beta squared quadrupole. So some of these have been measured already, not with very high precision. They could all be done better. Increase in the monopole, I think, is unmeasurable. And the order beta squared quadrupole, even although you might think that that tells you whether you're really moving or not, it doesn't. So as Miguel explained, and is in other papers, it's a quadratic correction, which even if you had an intrinsic dipole, you would still get the same order, what looks like order beta squared quadrupole. So it's sometimes called the kinematic quadrupole, but it's not. And this is described in a paper by Knox and Kamiankowski, and my understanding is they were halfway through the paper when they realized that you couldn't use it to figure out whether it's an intrinsic dipole or not, because they really thought that they were onto something, and then they sort of lost interest because it doesn't tell you that. There are, of course, related effects at other wavelengths, for like the modulation of source counts, which you've just heard about. Additionally, a completely different thing is that the sky appears dipole modulated on large scales, and this is an effect that was in the WMAP data and also in the Planck data and described in these isotropy and statistics papers in gory detail. It's certainly not caused by velocity because it's only on large scales. It doesn't extend to small scales. And it's a real effect, but the question is it statistically significant? So you can call it dipole modulation or hemispheric asymmetry. And since it's, at most 3 sigma, there's no difference between those two things. So they're the same effect. So basically the hemisphere on the left is supposed to look like it has more large scale structure than the hemisphere on the right. And you really have to kind of screw up your eyes and use your imagination to see that. So it's exactly not like this situation, where one side of the moon is dramatically different than the other side, which requires a physics explanation. So whether this requires a physics explanation is a question. So it's not the same as that. It's real but subtle. It extends up to a multiple of, originally people talked about 64 because they did it in powers of 2. So up to 60 or 70 in L. And it has an amplitude that modulates the sky, the power in the sky by about 6%. How do you assess whether this is statistically unlikely? So let me make 2 comments on this, and some of these things apply to other anomalies. There's a cosmic variance for dipole modulation, so you can work out what it is. So you don't expect the sky to have no dipole modulation because you've selected all these multipoles randomly. So it turns out that the fractional variation in power amplitude is this expression. So it gets smaller as Lmax gets bigger. The expression is about 5 or 6% for Lmax of 64. The modulation in the map is half of that. So it's about 3% for Lmax of 64. So you shouldn't be super excited by a 6% modulation because the expectation is 3. And it's like a chi-square distribution with 3 degrees of freedom. So it's a wide distribution. So I mean, that already makes you suspect that it's not that incredibly unlikely. But on the other hand, if you had a model to predict it, then it would be, and the scale was in there, then the statistics would be much more robust. And large scales are special, so we should keep looking. So a lot of us are excited by the promise of polarization, which offers independent tests of these kinds of ideas. So we're going to test for these kinds of anomalies in polarization data for sure, for example, from Lightbird. The second note of caution I want to say about anomalies is that it's very easy to convince yourself that a thing that you found is very special unless you're careful to assess the statistics. So this is, if people aren't aware, this is the most serious joke paper on the internet probably. So although it looks like a joke, it's hiding a very serious lesson. And the serious lesson is it's easy to think that things are very unlikely when they're not. So I looked for patterns in the digits of pi, which I think we all agree are random. And it's very easy to find patterns which, without being very careful, you can assign very low probability to. So they seem to be incredibly unlikely. And for the hemispheric asymmetry, so the thing on the left is how unlikely it is to get a dipole modulation of the amount that's seen as a function of Lmax. And you can see that the Lmax of 64 thing isn't even particularly extraordinary compared to the one that's at 40 and 15 and 200. So you're already sort of suspecting that this isn't anything at all. And for pi, I just took the first half of the digits of pi and the second half of the digits of pi. And it turns out if you add those up, they sort of deviate from each other in ways that look like they're quite unlikely. But they're not if you're careful to do the statistics. There are, of course, other dipoles on the sky, for example, the sources that Nathan just discussed. The surface brightness is modulated and there's aberration, which changes the solid angle. The result depends on the count slope and the spectral index. Early methods to try to do this involving the optical and the near infrared seem to find results that are consistent with the CMB in amplitude and direction, but as we've heard, recent estimates involving radio and quasars now appear to be too high, so we should continue to investigate. And I don't have any deep insight on this, but I know where my money would be if we're talking about bets. There are other dipole-related things. For example, the CIB and all the other monopoles will also have a dipole, and the amount of modulation depends on the slope of the spectrum and so on. So you get different ideas there. The CIB monopole is hard to measure, so people have suggested that if you can measure the dipole, and since you know what V over C is, you could infer the monopole, which would actually be a cool, inversion of the way normally it's done. You can talk about whether there should be a dipole in gravitational waves. There's dipoles in the neutrino background, even though we can't measure it. In principle, there's more than one neutrino background, and they would have different dipoles nominally. You can measure cosmic acceleration from the proper motion dipole changing with time in cosmology, and that's not completely out of the question to do with future high-resolution radio imaging of quasars and so on. There are papers on all of these things, and if people are interested, I can point you to the relevant references. I didn't write them all down here because there'd be too much. And then I can move on to, now that I've done the monopole and the dipole, let me talk about the quadrupole, but oh, it looks like I'm out of time. So I'm going to finish by giving you some suggestions for what you call the study of the quadrupole. And then I'm done. Thank you.
Okay, thank you very much. Maybe you can take one or two questions, if there's any.
I think I managed to finish on time there, which is astonishing.
Yeah, actually, you started at about 7 minutes late.
Yeah.
At least 1 minute earlier.
Douglas, maybe you can follow up on your octopole comment from, was it yesterday or the day before? So there was this anomaly at large angles. Right, you said that if you remove the octopole, right, that this essentially went away.
The quadrupole.
Right, that was it, right. So this is probably what you're going to tell us about now, right, in your slides.
No. Yeah, well, I could have done, but I definitely was. I mean, I could say lots of things about the quadrupole, but I don't have much to say about the hexadecapole. The point I was trying to make is that Dragan and other people have made a big fuss about how the correlation function is nearly 0 above 60 degrees. So fine, but we know that the quadrupole is low. So let me remove the quadrupole and calculate the correlation function just for L of 3 and bigger. And it looks completely different. Right? So the quadrupole affects all the scales. So you're no longer struck by the fact that it's 0, close to 0 above some scale. So it's totally dominated by the actual quadrupole that we have. So I don't find that very exciting. I think it's just another one of these things that you can pick things and assess how unlikely they are, but you need to assess how many things there could have been that you tested. But hopefully that makes some sense. I mean, try the exercise for yourself.
Okay, let's move on. Of course, we may have a lot of discussions after the final.
Yeah, let's discuss. Miguel has his hand up, but we can go to the discussion later, right?
I'll leave it for the discussion. No worries.
Yeah.
Okay, so the final last speaker is Luin.
Yeah, can you see my screen?
Yes, go ahead.
Okay. Thank you for the organizer. And my talk today is that the Hubble tension signal breakdown in FLRW cosmology. And this work is collaborated with Elin, Shahin, Chisen, Roya, and Orlando and Marco. These 3 papers our cooperation is based on the 3 papers. In this talk, I will argue that cosmological H0 is mysteriously tracking the CMB dipole direction across a host of different observations. Despite this those observations being in the CMB frame. And if it's true, we should reconsider the whole current cosmology, which is built up on the FLRW framework. That's the punchline of my talk. First of all, the H0 tension comes from the different observable results between the CMB and the supernova. The H0 tension may be a game changer for the modern cosmology because all of the H0 value, all of the local H0 value are biased higher than the Planck, such as this one. Naively, one may try to resolve this by changing dark energy sector. effects of which is more pronounced in the late universe, but this may not work, as we will see later. The FLRW metric, based on the idea from the Friedman, Lemaitre, Robertson, and Walker, they consider a homogeneous, isotropic, and expanding universe that is path connected. And this also written in every textbook, such as the cosmological principle, with the appropriate and the minimal matter content. That is the backbone of the standard model in modern cosmology. And this equation is the Friedman equation. We can see the right-hand side, if we given a time, all the parameter is a constant. So the Hubble constant, the Hubble parameter, the H0, should also be a constant. But all of this are based on the big assumption of FLRW. We will ask, is the real universe also isotropic? This is the CMB is a snapshot of an FLRW universe in the very high redshift. It's the most early information we can get from our history of universe. With the expanding and the cool down, the wavelengths of the photons have been redshifted to around 1 millimeter, and the effective temperature has decreased close to absolute zero. And the difference of the temperature we can see in the red and blue point in this figure only just 1 part of 10,000, but this result, this information comes from the background dipole has removed. So this signal is about 100 times larger than the intrinsic fluctuation in the standard cosmological framework. This is be considered generated from the gravitational effect of local structure. That means our universe is not isotropic on small scale. Objectively, in the Planck lambda CDM universe, this anisotropic had a special direction that has been mentioned by Subiers and George's talk before. There are also evidence from the Bok flow in galaxy moving. The dominant fluctuation causing the observed flow a single attractor, which contribute almost equal to the CMB dipole. This dipole repeller is predicted to avoid the effective in the distribution of galaxy. It means our local universe is not FLRW, and if it's anything, maybe mildly anisotropic, as that have been shown in this work have a very clearly observation. Dominic's talk on Tuesday also introduced the cosmic radio dipole, which is given by the SKA observation. The red point, such as the red point in this one and the red in this one, are all radio source, and the blue point are the local source, which can be excluded from the analyze. And we can see all of them have a special distribution and have a similar dipole direction. Subir's talk and Nathan's talk also introduced this for the dipole in the Cat West. This special experiments. They observed the quasar, and we can see this is data distribution with redshift. Almost of quasar data is distributed in the redshift 1. we can see this figure, the dipole direction in the galactic coordinate is in the 2 sigma uncertainty range. And this also shows a different result from the catwise and the CMB results. The observation recently extend the cursor at almost 5 sigma, and the dipoles agree with the CMB direction, but not magnitude. If the anisotropic is pronounced and real, it may be seen in the simple way using H0. Interestingly, if true, this may turn almost 100 years of Hubble Hunter on this head. As Sherlock Holmes have said, when you have eliminated the impossible, whatever remains, that must be the truth. In the next, we will introduce our work and our fitting results. Within certain assumptions, we give a recent upper bound on the H0 value in any FLRW cosmology. This is the fitting result in our paper. We give the H0 is 71, and this paper have published in CQG. In fact, we rule out the resolution to H0 tension, which only rely on the late physics. And this is the H0 constraint from the TT Cosmos lens as a function of lens redshift. We can see all the data point is under the 1 sigma uncertainty. And this figure is from our paper. We can see the red point is from Quasar data. We give this is H0 value from Quasar data. And the black point, this one is the CMB dipole. The background, the yellow one is galaxy count. We can see the spectral distribution of this H0 value have relationship with the density of a galaxy count. And then we will introduce the spatial direction in the non-FLRW. We use this equation to test the H0 value distribution, and the B is the average of H0 value if it have a special direction of this Hubble constant. The sigma will be non-zero, and if it's totally isotropic, the lambda is back to 0. And this is the spatial direction in large scale. We can see the D and R as longitude and altitude, such as this one, longitude and altitude distribution in the sky. And if and in the later we will add a weight to this spatial direction. For the real data from the supernova, we found the sigma is equal to 1.18 in the Python observation. And this is supernova's observation. We can see the luminosity sometimes is fade slowly, sometimes is fade fast. If we give it a correlation, a correction, the luminosity distance will have a more simple form. And this equation is to describe this distribution, and it can be used to in any kind of models. And to get the H0 value, every point can give a H0 value independently. And this is a special parameter in the supernova So in this equation, we can see the degeneracy between the MB, this parameter, and the H0 value we will show later. This is the special direction, special distribution of H0 value we can see, and in the green color, it means the average value for the isotropic universe. But we can see in the real universe, there is a special distribution for the red and blue one. That means the different distribution value of H0. We can see the CMB dipole is in this part. It means the CMB should have a larger value than the average. This is based on the distribution of, this is based on the Python data in the full sky.
Luke, may I interrupt?
Yeah.
There is a question about this equation. What
Yeah.
are A and B?
Okay. That is just a different value from 2 points. We can also consider it is a north part or south part, or just a different 2 points in any different 2 points.
Okay, please go ahead.
And for this one, we can see this is the spectral direction, and in this part, we add a weight for this direction. This is we can see the distribution of the Python in the supernova data, and this is the mock data in the central value of 0, and the red color is 1 sigma uncertainty. We can see, and the blue and the black one is the real data set. We can say the real Python data set. It have it is out of 1 sigma uncertainty from the lambda CDM value, from the theoretical value of supernova. And we also fit the flat lambda CDM model to the original data, and X-ray best fit value is 70.03. In the next, we will show the evidence from the quasar. The quasar is extremely luminosity active galaxy nuclei, just like this figure. And this is powered by supermassive black hole. There are a lot of observation from the quasar recently. It have more than 2,000. And we can see the distribution with redshift here, and almost the data is based on 1, almost the same with supernova's results. And this figure shows the distribution of quasar observation in all the sky. And this also shows the result of distribution of H0. We can see in the quasar data, the CMB dipole is also larger than the average, and the background, all the data set is also shows there is a special distribution from different range of the sky. And this is equation for this quasar data set. We can say some is luminosity, some is fluctuation, and the beta is a special parameter in the quasar data set. So based on this equation, we can see the degeneracy between the H0 and the beta. That is special in quasar. This is the ratio between the angular diameter distance measured from the BAO, and this is Dicey is the golden star in this point. We can see this is out of 1 sigma range, and this is the lambda CDM. We can see it is out of 1 sigma range with the lambda CDM, and it prefer lower value of the DL. We can also see the special distribution of the quasar from the quasar data set. We have introduced the beta is a special parameter, and we can see the distribution of it. And we also add a weight for this special direction. This is also mock data. If it's isotropic, there should be the beta should be back to 0. But from the real observation, it has been out of 2 sigma uncertainty. It's a very powerful evidence for the anisotropic universe. The last result we will see is the is our fitting result from gamma ray burst. The gamma ray burst has been observed in the distant galaxies, such as this figure. They are the brightest and most electromagnetic events in the universe. And there are not too much observation result from the gamma ray burst. Almost is around 100 data point for the GRB. We can see the distribution for this one. They are most crowded in the redshift 2. That is a little higher than the supernova and the quasar results. And this is the distribution for this 118 data points. We give the result from the, we give the equation for this gamma ray burst. This alpha is special in our in the calculation, and we can say it's degeneracy between alpha and H0. And in this result, we can also see the similar figure, because all of the 3 data sets, supernova, quasar, and the GRB, show the same evidence for the special direction of the H0 distribution. This result, the black line is a real data set for the GRB, and if the alpha back to 0, that is isotropic evidence. It is isotropic events, but from the real observation, we can see that it has been out of 1 sigma. Between 1 sigma and 2 sigma. So the value for the real data set, the sigma summary is 7.89 in this point, cooperated to the in this black line. So that's the summary of my talk. Based on the evidence from other people's work and our work from supernova, quasar, and GRB, the universe may not be isotropic and homogeneous. If the H0 is tracking the CMB dipole direction, despite being in the CMB frame, something is fishy. Depending on data, statement is in the 2.4 to 4.5 sigma window. If it's true, the Hubble tension is only a symptom, not a problem. We look forward in the future there are more observation results that can give more evidence for justify this problem. Thank you for your attention.
Okay, thank you very much. So, are there any questions to Lu?
Yeah, so I have a question. So yesterday we were discussing a lot how to properly, this discussion with the talk of Tamara Davis, and how to properly correct from heliocentric redshifts to cosmological CMB-centric redshifts, that some of the catalogs provide only an approximate formula, which is not really very good at high redshift. Are you checking that you are really going to the proper CMB redshift for all these data? Because this would clearly produce such modulation.
I see. That's we discussed yesterday, but in this work we didn't consider too much for this CMB redshift. So so in this work is no, but maybe in the future we will also consider this and discuss in our project.
Okay. Pavan, do you have a question?
I can ask a second question. So here in the summary, you're saying 4.5 sigma.
Yes.
Which result gets you 4.5 sigma? I didn't see in your. Is it the joint? You're just multiplying how you get 4.5 sigma?
The first one is from the this point, this Quasar result, and the other 4.5 sigma is almost from Subir and other people's result for Quasar and the Bakru, some others.
Actually, Miguel, it's basically just a multiplication of the probabilities, right, based on simulations.
Yeah.
And I mean, you'd have to go over 4 sigma, you would need to take the GRBs into account. They're a little inconclusive. So basically, so I think if you just look at the lensed quasars plus the supernovae, you're at 2.4 sigma. So you're already over 2. Then with the quasars, you're over 3, depending on how you want to treat the quasars. And then you can go beyond 4 with with basically the GRB samples, but the GRBs themselves, we need to figure out what's going on. So this is why we're quoting a range 2 to 4 sigma, but it's based on simulations.
And how much is this result independent from, like we were hearing before from some Nathan Secrest, right? So there is a larger than expected dipole in these data anyway. So is it?
Lou, you answer?
You can.
No, over to you. Let's see what. Okay, Miguel. So I think what's nice about the quasars is that it seems to be consistent with what Nathan is saying, right? And they're very deep. So I would be interested to know what Tamara says about this. What I would like is a result in the literature where basically people say beyond some redshift, we're in CMB frame, quote unquote. And then, because typically what the quasar people do when they do quasars as standard candles or GRBs as standard candles, people just neglect this change of frame. But since the change is quite small relative to the redshifts, like if you're a redshift, 0.3, 0.4, 0.5, or even beyond that, 3, 4, 5, wherever you are, right? These should be very small corrections. And then those corrections have to go through the luminosity distance and then to whatever, magnitude. It's hard to imagine them making a big difference to this result.
Let's see. But anyway, if you know that
we should check.
If you know the source, it's a simple check. It's a simple correction, I guess, right? I've done some work in Supernova. you just need to have an angle, and then you know, I mean, assuming of course the velocity is known, it's just it's a simple correction to do. I don't know, maybe it changes a bit. I was thinking.
Yeah, so but basically the luminosity, like let's take a luminosity distance. Luminosity distance is like the integral of 1 over h of z roughly, right? Now, if you change a redshift by a small amount, which I guess is 1 part, I mean, what's it, 10 to the minus 3 or so?
Yeah,
It's already at 0.7. That's going to be a very small difference in that integral. And then you've got the fact that it's going as 1 over e or 1 over h of z, right? I mean, at high z, we're using
it's
lambda
1 plus z times this. Yeah, it's 1 plus z times this. Whatever correction we have is 10 to minus 3, as you said, and then
Yeah,
I mean,
so-
it's more, but I don't know.
Yeah,
I don't
it's hard. It's hard to like. We should do it. We should do it. But given the differences we're seeing in beta, which is, I guess, beta is essentially degenerate with the log to base 10 of h0. Yeah, we should check this. But
Yeah, I think Tamara David has a nice paper on this, which shows exactly what's the formula that you can just, correct. This is doing that, and that's the beaming effect, and this it's both effects, right? The beaming, the gravitational redshift, and that's it. It's just
exactly. So it's very easy to do this, but I don't expect it.
The harder part is knowing what is the data, right? Because as we discussed, some of the catalogs of supernovae or I don't know KSOs and they're not very clear sometimes what's the redshift they're using. So
I think what surprised me is they're actually doing cosmology in heliocentric with heliocentric redshifts. So typically they don't correct at all.
Yeah, but that will give you a clear. That will give you a dipole in the direction of the dipole, right? So I don't know if it's negligible to what you see. That's what
Exactly. I mean, again, we're talking about very small numbers, right? If you're at 0.7 and beyond, then you're looking at a correction of 10 to the minus 3, like in the overall factor, right? Even the luminosity distance. In principle, it could, but we should check.
But Yoen, are you sure that we are using the heliocentric redshift? I thought that they will correct for the motion of the sun and the motion of the sun against our galaxy.
I'm using whatever redshifts Risoliti and Lusso quote in their, but I don't think they're they're not the usual redshifts in CMB frame.
Oh, it's not a CMB frame, but at least it's in the galactocentric frame.
It may well be. It may well be. But again, these are. I mean, there's lots of people who use these data sets, and I think they just take the redshifts at face value.
Okay. Well, there is a question by Pavan about the quasar sample. So his question is if the quasar sample's distribution is already anisotropic, so how much confidence can we put in the result? So Lu?
Yeah, that is a lot of evidence for the quasar data set is a different distribution in the north and the south part. How much confidence we put in the result?
Pavan, so basically in FLRW, orientation is irrelevant. Like once you're working in FLRW cosmology, typically people don't even show these maps. It doesn't make any difference.
Okay, so
if you found that an anisotropic distribution gave you anisotropic cosmological parameters, you would have a violation of the cosmological principle, which is what we're seeing here. I mean, so FLRW basically just suppresses orientations. We wouldn't care in what direction anything is.
So where this quasar sample come from?
So I guess it's part of SDSS, right? Yeah. So basically, Risoliti and Lusso are compiling. They've been slowly building a compilation of quasars. So there's various cuts that they go through. But it's all based, if Lou has where's the lumen, there's a relationship in luminosities. Oh yeah, so basically on slide 18, I guess. So basically it's this upper relation here in luminosities in X-ray and UV with two parameters, beta and gamma, that they're assuming holds at, over extended redshifts. And they have a series of papers and other people have also looked at it. So it seems like gamma is very robust. The slope is robust in this, but beta itself, there could be some evolution in beta. If you read our paper, we do address this. Okay, maybe we're in the discussion, are we?
Yeah. So maybe we can repeat some of the discussions in the chatting window, because not everybody have looked at. So there was some discussions about the smoothing of the quasar sample in Nathan's talk. So
before we go there, can I ask a question? I had my hand up.
oh, okay, go ahead.
I see we are not going by raised hands.
Yeah.
In this work, you are relying on the fact that quasars are standard candles, if I understand correctly. But we don't know that they are. And I mean, I think this partly answers Pavan's question from the chat window. I think he is asking about the fact that the distribution on the sky is inhomogeneous, but that's irrelevant. And even if you were measuring clustering, it wouldn't be as important if you take into account. But I think here you're looking at their fluxes and stuff like that, right? And how that, like you would for supernovae. But I wonder, I mean, this is a big time conjecture, right? That they are standardizable candles. It's not really proven. So.
Yeah, but I don't know what you would do. I mean, so I think quasars are essentially where supernovae were in the 90s, right? So we didn't know about shape, we didn't know about color, we didn't know about the correction for the host mass or the mass of the host galaxy.
Supernovae won the jackpot lottery in the 90s. They got maybe incredibly lucky or something. It amazingly turned out that they are standardizable, but who knows if that's ever going to repeat again. Right.
So, but there is an intrinsic dispersion parameter that basically covers all of this. So, I mean, there is an analogy between the two here. Now,
as somebody who remembers the 90s, the supernovae were already pretty much standard candles compared to quasars in the 90s. I mean, the details had to be worked out yet. But
right. So
quasars are nothing like standard candles.
The Phillips relations for 93, I guess. So years before the main results.
Yeah, the Phillips result is 93, right? So basically, even when we look at the discovery, I guess, I'm just saying that the corrections for shape and color were probably not there,
well,
but still.
Fritz Zwicky knew they were very similar many decades prior to Phillips, so that was, but I mean, maybe this history, I don't know how important it is. I'm just wondering, I heard you guys arguing over what sounds to me very fine points about the redshift, very, very fine points. But isn't by far the biggest factor the fact that you have to?
I think I agree, right? So basically, if quasars are standard candles, we have a result that's consistent with Nathan. I mean, so it's not our proposal. This is Risoliti and Lusso.
Other people have claimed. Yeah, I know. Yeah.
No, I mean, okay, if their claim holds up going forward. Actually, what's very interesting is basically beyond some redshift, the luminosity distance is low relative to Planck lambda CDM. Actually, there was a very interesting paper out of Buffalo where they seem to get some very similar results, again, trying to use quasars, again, trying to standardize quasars. So yeah, I mean, there are other techniques as well, but you just can't get as large a sample. This is essentially 2,000 quasars, right, or thereabouts. And Dragon, one small point: we're only interested in H0. So the cosmology, like basically the E of Z part of this, we don't really care about. We're looking at variations in.
No, but that I'm not sure that helps because you're relying on this like you can compare. So I don't know that it matters how many parameters. And I see once the Konstantinos is saying in the chat, which is a weaker statement than the fact that they are standard candles. But still, I mean, it's kind of like an unproven conjecture, I guess. I don't
Right,
know.
but so basically we have a number of things that are pointing us in the same direction. We have the lensed quasars, which again is not our data, which is this, you know, strong lensing. You know, this Holy Cow, TD Cosmo stuff. We've got type 1a supernovae and Pantheon. Like, so that is a genuine trend there in Dan Skolnick's, you know, Pantheon sample that Dan wasn't aware of. And then you've got the quasars, and of course they're probably the only ones that are statistically significant. And then GRBs, you can certainly find similar trends, right? So if you are finding a separation, like if it comes down to the bread and butter of cosmology, which is basically the Hubble parameter, and you're finding that H0 is larger in one hemisphere over another, and you should be in CMB frame, then cosmology has a problem. It's just a matter of time before everybody sees it.
I mean, it's just hard for me to fully appreciate what you mean when you say there's all these things pointing in the same direction. So what?
Okay.
What do you think? Because I mean, you must have some new paradigm in mind that they're all consistent with.
Yeah. Okay.
No?
So let me call them coincidences, right? So okay. So we've got some weird alignments in CMB that are pretty weird. We've got So Damien gave this Hutzenmaker's. Damien gave a talk yesterday, which was about these quasar polarizations and alignments there. It also seems to connect to the CMB dipole. Then we've got Nathan's results. We've got the radio, cosmic radio. The dipole and the radio galaxies. We've got Costas's results at lower redshift. There seems to be a whole lot of stuff pointing to the CMB dipole direction.
But I mean, to me,
observables that are tracking it that shouldn't be tracking it.
Just to carry on with the same train of thought and go big picture here. If you're claiming that all these things are related and they're all part of some way of showing that there's some different paradigm, then if one of them turns out to be nonsense, then the whole house of cards would fall down. But I don't think that's what you're saying.
No, I'm not saying that. I'm saying that, like, so basically.
And therefore, I think that these are just a bunch of coincidences until you have a framework in which, and the framework would have to be robust enough that if something if one of the pieces of support of the framework proved to be incorrect, then you would reject the framework.
Good, Douglas. So at the moment, as I see it, cosmology has a H0 problem. And cosmology may even have a cosmic shear problem. Now, you can kind of ignore these and brush them under the carpet, but, Adam Rees is going around giving talks. H0 tension is developing, people are trying to solve this problem. They haven't been able to solve it.
Well,
and one of the few...
I wouldn't brush them under the carpet or ignore them. I would continue to study them, but until there's the thing to replace it with, I don't see how you can say that they're all pointing in the same direction. My guess is that there's no way that all of these things are correct, because they're not consistent with some other paradigm either.
But there's a lot of them, Douglas, right? These coincidences. Let's call them coincidences.
But if one of them turns out to not be correct, are you still happy that there's a problem?
Oh, I would back off on as these results basically disappear. Like, in principle, we should get rid of all of them and then come back to the H0 tension problem, which is already quite a serious problem.
Dipoles, right? Some of them are axis, not just dipole. I mean, directed vectors. They are axis. They indicate axis. Like, for example, from CMB, they indicate axis of anisotropy rather than direction. So you cannot say whether it is towards the CMB or away from the CMB. That's what I thought of asking Damien in his talk. He showed this clustering in opposite directions, which are prominent. So the statistic might have been will give an axis rather than actually a direction. And I have a follow-up question to Douglas. So you mentioned about this. Yesterday there was a lot of discussion regarding whether there is any intrinsic dipole or not. So you almost suggested that there is no intrinsic dipole at all except for our relative motion through CMB rest frame. So can you throw some light on that? Can you elaborate on that a little bit if you have any thoughts?
Who am I talking to, actually? Sorry, I've lost my...
Pavan, right?
Yeah.
Okay.
Was my question clear?
Yeah. No, I'm just wondering who I'm talking to, just so that I
Okay.
can orient myself. I mean, the only point I was making was if it's adiabatic fluctuations, then there's 1 degree of freedom, and you don't get to have a CMB frame that's different than the matter frame. So you require something like isocurvature perturbations on very large scales. But we know that it's adiabatic perturbations on basically all the scales where we've probed the CMB well. So you'd have to have that there's a giant isocurvature perturbation that's like a slope across the Hubble patch, which is possible, but it seems, it's not the simplest explanation. The simplest explanation is it's all adiabatic. So that's the requirement. It's not easy to do to make an intrinsic CMB dipole.
Okay.
Can I jump in here in this question?
Yeah, Miguel, I think we're mostly agreed on this point, so please.
Well, let's see. So I'm not 100% sure, because what you say about, in the diabatic case, there will be no intrinsic dipole. I also thought this for some time, but I'm not sure I think exactly this way now. And my reason, I try to do a strawman argument here first, so everyone is on the same boat, and then let's see. So in the adiabatic perturbation scenario, what you have is that, the perturbations in velocity and density, they are in phase, right? So they are correlated. So if you have a region of the sky, which is, let's say, hotter for some reason, because maybe it's denser, it's also a perturbation of velocity must be in the same direction. So therefore, it's a gauge thing if you call it intrinsic or velocity, right? So this is I think the strawman argument for it not being possible to measure in the adiabatic part. But if you talk about aberration, for instance, right, or these Doppler couplings or modulation couplings, whatever you call, fundamentally, these are second-order perturbation quantities. They are not first-order perturbation quantities, right? Aberration, it's we describe it in the simplest scenario as a coupling of a velocity term, 10⁻³ plus the temperature contrast, 10⁻⁵, and then you have this 10⁻⁸. But it's fundamentally a second-order perturbation, right? And I think that the simple argument that you cannot detect intrinsic components because in the linear perturbation theory, these things are in phase, does not hold anymore in the second order perturbation. And therefore, you can talk about physically different scenarios. In one of them, you do have, let's say, just a velocity, really velocity, what I would call, and that will produce you the aberration pattern, the dipole pattern, this Doppler couplings, everything. But you could have a scenario where even if your potential, your primordial potential is adiabatic, that you do not have the same aberration pattern that you would have if you just had the velocities, if you have a density fluctuation, right? And it's not completely degenerate anymore, because then, the aberration thing, it looks like really like a dipolar lensing. It's an integral along the whole trajectory of the photon. It's not something which is only on the less scattering surface. So I now have the impression that even if it's adiabatic, they do differ in the second order perturbation quantities, and therefore you don't expect, in principle, the same aberration pattern if it was not a kinematic thing.
Yeah, I think that's, I think you're talking about the subtler, deeper question. I was just talking about the high level question, which is, what would it take to have an intrinsic dipole? I'm saying, I think you would have to have an isocurvature perturbation on large scales.
But maybe then we're discussing semantics. But you see, the way we measure in our paper, or we propose to measure the intrinsic dipole, is basically by taking two observables. One of them is the dipole itself. The other one is these aberration couplings, for instance. And you make like a simple subtraction of them. Then if you neglect a bit the lensing component of CDM is negligible, then that is my intrinsic quantity. And I'm saying, if you just say the difference, there can be non-zero even if your perturbations are adiabatic. Now, maybe you don't call that, intrinsic dipole, but I think it's something which is there in the less scattering surface, and it's some new degree of freedom, if you want. It's no longer 1 degree of freedom only. So whether you call it intrinsic dipole, or you're just, saying, well, it's this quantity which is, gauge independent, maybe it's more semantics in the sense.
But Miguel,
but at the level of power spectrum, when you consider beta square, I mean, the contributions come only to power spectrum at the level of beta square. So how it's already 10 power minus 6, contributing 10 power minus 6 to that. So how well that is detectable? I mean, at least the kinetic one, forget about the intrinsic one. I'm not sure if you are referring to how is it what is the kind of your estimator? I could not attend your talk yesterday.
No, it's okay. No, so I'm not talking about the 10 to minus 6 corrections to the spectrum, not the 10 to minus 6 quadrupole. The way we detect is the coupling of the 10 to minus 3, which could be the velocity, and the 10 to the minus 5 normal perturbations. And this coupling happens in all scales, all L's. So you can imagine this is a LL plus 1 couplings. And there's those 10 to minus 8 couplings, those are the things that have been measured by the Planck collaboration and by my group. So this is aberration couplings and Doppler couplings.
Okay, gentlemen, maybe we should go back to the other questions which was put on the chatting window. So there was a question by Jenny Wagner to Nathan and Douglas. Jenny, can you speak?
Yes,
Yeah.
I was wondering, but this was long ago. I was just wondering whether people say when we have a dipole and what is the rest of the structure, we could make a statistical test in order to see whether the rest of the structure, which may left, is just random or has some other distribution. That was just a comment. But following up on that, I'm wondering, Nathan, do you take into account the Malmquist bias in your fluxes? So what about the effects of lensing? My gut feeling is that lensing could be equally distributed, giving you the same direction, but that it affects the flux cuts so that you are changed, that you get changes in the amplitude.
Yeah, so the lensing, the effect of lensing is something that I've actually been thinking about all throughout this discussion. And I haven't seen an estimate. I mean, if we assume that there is only one dipole and that it is purely kinematic, then I suppose that the lensing would be by the matter that is also whatever is attracting us and inducing our motion. I could be wrong about that, but I haven't seen any estimate for what boost or what factor that would multiply apparent fluxes by. I would be a little bit surprised if it was by a factor of 2, but I just haven't seen that analysis. I didn't catch if you had. What was your first question again, or comment?
No, that was just that you can subtract the dipole and then you can have a look whether the remainder comes from a random distribution, just like a statistical hypothesis test.
Oh, right, yeah. So early on, we did see that there is sort of, if you collapse along the dipole direction, the pixels, the sky pixels are Poisson distributed. But there is some broadening that I assume is cosmic, due to cosmic variance. But we've not done any further analysis than that.
Mm-hmm. And I think concerning back to the lensing, I think maybe you have a chance to find out where the culprits are. For instance, when you say that you just want to have quasars below a certain redshift. For instance, the higher you go in redshift, the more likely it is that something gets lensed. So if you make a cut like redshift 0.7 or so below 1, and then you have a look in how far this changes your amplitude. I mean, the significance will go down, of course, but the question is, are the high redshift quasars causing this huge amplitude, or is there some other systematic effect that may be traceable?
Yeah, and unfortunately, despite how critically important they are, there's still really not a proper sort of full sky deep spectroscopic survey, and so the number of objects, we don't have spectra for all of our quasars, but that is definitely, I think, a test that that would be worthwhile to pursue if it becomes available.
All right.
Thanks a lot.
Yeah. Okay. And there are some discussions about the smoothing and what's the size of the smoothing and
Right. So
whether this was used for the analysis, and the answer was quite simple, right?
Right. Yeah. So yeah, the smoothing was just as a kind of sanity check. So we were getting these results that were quite high at statistical significance, and so I'm very much an observational astronomer. I like to actually look at my data.
Yeah, otherwise the smoothing would introduce some correlations and you have to worry about pixel correlations.
So yeah, none of the analysis was applied to any kind of smooth map. So the sky pixels are independent. That's right.
Okay, but just to put this all in context, Jenny, right? So if you ask anybody now, right, whether or not the matter dipole aligns with the radiation dipole, I would say, okay, it does in terms of direction, but there is a discrepancy in the magnitude. And it seems to be a fair, is this a fair statement?
Yes, yes. I was wondering, like, can we find out where this amplitude discrepancy comes from? Like, is it just a high redshift effect? Is it a sampling effect? Can we just track this down in our data? That was my hope, but I do not know whether this works out.
I mean, the only thing I could say to that is just to reiterate that the anomalous dipole that we see, or the anomalous amplitude that we see, is consistent with previous samples that were more or less completely independent in terms of their objects than the specific AGNs. I forget, there was an earlier question, but radio AGNs do tend to occupy different galaxies than the mid-infrared quasars. Radio AGNs tend to be in more central, early type massive elliptical galaxies, while mid-infrared quasars tend to be in spiral galaxies and ongoing mergers in a relative sense. So, and their redshift distribution is a little bit different as well. So I can't really answer that question beyond just making that point.
Okay. And there is a comment by Konstantinos to Douglas. Konstantinos, can you speak? If not, I'll just read it off. So the comment is, clusters also see a dipole with X-rays and with the Planck TSG values. The latter actually see a 900 km per second bulk flow up to 500 megaparsec, which is completely in contrast with the KSG results. I fully agree.
I mean, I missed that this was the discussion. Was this yesterday or the day before? No, day before, right?
No, this was today.
No.
The comment.
Referring to the talk that was who gave that talk? No, I'm trying to remember.
It was to Douglas.
So Costas gave the talk, right? So Costas' talk.
So he's referring to Costas's talk, right? Where he pointed out that by using scaling relations for X-ray clusters, you can derive a different dipole. So his claim was that his thing is much simpler than the kinetic Sinev-Zeldovich effect. I don't agree with that. I think the beauty of the KSZ effect is that it's sort of independent of lots of selection effects. The problem with it is that it's very low signal to noise. So we were, by using 1,000 clusters, you can get a reasonable signal to noise for the whole sky, but cluster by cluster, it's very low signal to noise. So I think it's a very simple experiment to do. And there's a limit on the dipole that you get. So my guess would be if you get a different dipole from using these properties of X-ray clusters, it's all to do with selection effects and biases and so on. That would be my guess, but I mean, I haven't done it myself. But I agree that it's interesting that they're different, so that it should continue to be studied.
Douglas, just this is essentially a low redshift thing, though, right? A low redshift check on the dipole.
Which,
So this KSV test, right? So it's
Yeah,
something you
you-
touched
you-
upon on your talk, right? Whether or
you
not
need a big cluster sample, so you can't only use clusters that are redshift 1 or something, because you wouldn't have enough clusters.
Okay.
But I mean, clusters are typically quite far away. I mean, they're not at redshift 0.01. Right?
Okay, so you mean at 0.1, right? Typically at
They're
0.1,
like 0.1 or something,
0.2, right? Okay.
Yeah, but if you just use the ones above redshift 0.5, you would remove most of the samples. So.
Right. So Nathan's results are basically presumably based on quasars at very high redshifts, right?
Nathan's, right? But
Yeah.
not
Yeah.
Costas's.
Yeah.
They're
Okay.
Probably more or less the same cluster sample. I don't know exactly.
Okay.
But it's interesting that those disagree. So that should be investigated further. I haven't-
Right. And there is a question by Pavan. Can you repeat the question to Nathan about the size of the patches used to estimate the clustering?
Oh, he answered it in the chat. So he doesn't about some 250 square degrees or something like that. So I have to check that patch and see for myself. So he doesn't have a ready answer, it seems. Am I audible?
Yeah, that was perfect,
Oh,
right?
okay.
Thanks.
So the comment by Nathan about the redshift distribution, I think he gave exact numbers. So redshift came from EBOS portion of stripe 82, 250 square degree, something like
Yeah,
that.
I don't have the exact number. It may have been closer to 260 square degrees. But I don't remember recording the exact square degrees in the paper. So I'd have to go back to my file and actually find it. So I don't
My
quite
overarching question was that, like, what is the patch size to infer actually a dipole, so that you can dismiss a dipole contribution due to clustering, as you say. That's my overarching question.
I'm sorry, I didn't catch the first part of that question. What was the first part of the
The
question?
overarching question was essentially to see, like, what is the size of the patch, so that you can actually reliably estimate a dipole, so that you can dismiss its contribution. That was the purpose of this exercise, I guess, right? From the whole sky, you had some dipole measurement, and then used a patch to estimate a clustering dipole. And what is the size of the patch, so that you can reliably estimate a dipole in order to dismiss that.
Right.
Yeah, that's what my overarching question was. So if you have any comment on that, so that would be nice.
Yeah, I don't have any, I think, comment beyond that. There was some on the order of about 8,600 sources that we were able to get spectra for. So that, in terms of the statistical sample, that's where we're at. And then we derived the estimate assuming standard lambda CDM for what the dipole clustering dipole contribution should be to our found result, and it was a factor of 65 less than what we found. So we estimated that it was essentially negligible, and that makes sense because the mean redshift of our samples on the order of 1.2, so it's quite high.
Yes. Perhaps I should check the paper to get proper insight.
So we are now going into the talk by Lu, and there was a question about the degeneracy by, again, Pavan. It's a degeneracy between M and H naught. What is M here?
So capital M is the absolute magnitude. I think she mentioned small m, apparent magnitude. So I was just trying to correct, or when I was just querying, she meant probably, Lu meant probably capital M, but not small m. That is apparent magnitude. This is a minor.
So Lu, do you have answer to this?
We just get the difference from the M, and if M is and we have shown the M is also have the special distribution, special direction, and that is totally can be distinguished with the 0 with the lambda CDM, so that we can see it's a degeneracy between the M and H0. Is this okay?
But is it there in your slide, in your presentation, that plot, that yeah, that plot? I might have missed it.
Okay. Yeah, the first result is based on this one is the result of M, and we can see that is much larger than 1 sigma for the difference for the degeneracy.
Like if you go to the, I think, 2 slides before, I'm just talking about the distance. I was just referring to the distance modulus formula. So, and here,
Slide 14, Lou, right? I think it's
yeah. This one.
Yeah,
this is the usual formula, right?
Yeah,
Right.
this is should be capital M and H naught, right? It is not small m and H naught. So that's why I say it's a minor one.
Oh, degeneracy between, yeah, of course, there's a typo, right?
And I was kind of from her talk got the
Yeah,
impression
that's fine. Good.
There's an asymmetry in the
yeah.
MB also.
So the MB should be
There's a
big
typo
M.
in MB also. So
Yeah. Good.
For a question.
yeah, sorry to make it sound big.
All right. And about this indices A and B, Yoin answered that this is 2 hemispheres. So these hemispheres are defined by the dipole coordinate. I mean, one in one hemisphere at the pole of the hemisphere is the dipole.
Yeah, so
many hemispheres distributed across the sky.
Exactly, we chose hemispheres across the sky. So these are actually just scans on the sky where you move the vector, and each time you move the vector, you're basically just constructing a hemisphere.
Okay.
2 hemispheres, one aligned and one misaligned. And then what we see is that basically, okay, for the CMB direction, you're finding, or anything close to the CMB direction, you're finding slightly higher H0 values at low significance, but across multiple observables, which makes it fun. So interestingly enough, if this is a real variation or a real trend, and the people who are going off to measure H0 locally, the distance ladder people, you can ask, what are they measuring? What is this point of this discussion between TRGB and Cepheids as calibrators? Or Hyungmok, even like going to LIGO, will LIGO be even able to determine H0?
Right. So it's
going forward, right?
Yeah.
So I think Maurice put a comment regarding the uncertainties in the H0 discrepancy that is being shown here. So perhaps that answer is in the equation for sigma, because it is being normalized by the error. So that discrepancy already goes in there, and from there you infer the sigmas. Is that correct, or am I wrong? There is a comment by Morris regarding.
Yeah, so there's a weighted sum. We're using a weighted sum basically because there's some ambiguity over the dipole in the matter, the matter dipole, right? So this is just some way of compressing the heat maps into some numbers, which we call sigma or something. And then we're basically quantifying how often do I get that number in, in simulations that are consistent with lambda CDM. And roughly 1 in 10, let's say.
Yeah. No, especially the, yeah. Yeah, perhaps, yeah.
Okay.
And Maurice, are you here? He left a question saying that there is always some discrepancy in central value in this differentiation by hemisphere. How do you assess the result is meaningful?
This is the question. This is the comment I was referring to. Maurice.
Sorry.
This is the comment that I was referring to by Maurice. The discrepancy perhaps already went into that delta H's that are in the definition of sigma.
Exactly, that's it. So it's the weighted sum and then the simulations, right?
But of course, Maurice have to say for himself whether he agrees to it or not.
Okay. It is some, yeah, okay.
He's not around.
Okay, good. Is there any more questions or comments? Okay, so I think we're more or less done, are we?
I do have a question. I was waiting. As we are going through the chat, but I have a question, so if I can. So to Nathan, so it's related to the question that Douglas Scott was raising, in the sense that you showed a plot of the what's the dipole in the in the source density there, and as Douglas was saying, it looks like there's more than a dipole. So, and this was also, I think, asked in the chat a bit indirectly. So if it is really a breakdown of the cosmological principle, there should be just a dipole, nothing else, right? So did you, I mean, I don't know if you can try to fit a quadruple there, because then you have to define what the quadruple mean. But I don't know if you thought about this, trying to fit a quadruple, so if it's 0, or trying to just do, as someone suggested here, testing for the Gaussianity of the, if you just remove the dipole.
Right. So we did attempt to fit a quadrupole, and the effect on the found amplitude of the dipole was fairly minor. But that being said, I agree that it's not the distribution we're getting is not a perfect dipole. But nonetheless, at least my understanding is that if there's even a dipolar component that is of the amplitude that we find, that is pretty strongly in violation of the expectation from lambda CDM. So I really need to emphasize that I don't feel comfortable commenting on what I think what I think is the physical nature of what we are finding. I can only state that statistically speaking, what we find is extremely unusual.
I understand, you're ruling out lambda CDM if you take that at face value anyway, but if there's a large quadruple that you expect to be 0, then the explanation cannot be just some breakdown cosmological principle. It can be, I think that's what I'm saying, maybe it could be hinting at systematics, or it could be hinting that you have different physics, which is beyond just a dipole. That's
yeah,
but I didn't get. So the quadruple, is it consistent with 0, or you said it was not consistent with 0?
It's I'm going off recollection here, but from what I remember, it was marginal. It was not something that we found to be worth pursuing further.
It may be that
but Nathan, what is the direction of that quadruple? I'm sorry for interjecting here. What is the direction of the quadruple that you infer? Is it same as the dipole?
No,
CMB dipole, right?
I think it was, yeah, I believe it was sort of roughly, it showed some kind of rough alignment with the galactic plane. but don't quote me on that because I don't remember exactly.
Because
It was not, I remember that it was not aligned with the CMB.
Because always you may find a dipole or something which is real, but perhaps there is a quadrupole which will be non-zero for a given realization, and then it will be consistent with expectations. I mean, marginally, as you said, that's what I seem to understand. Because I remember Planck also made a measurement of this quadrupole modulation of the power spectrum, and that was consistent with expectations within the error bars. I mean, it's not like zero. Like for example, P of k is modeled as P0 of k times 1 plus alpha k hat dot n hat square. So that alpha is kind of non-zero, but it is within the error bars, if I remember correctly. So there is always this non-zero quadrupole that would be there randomly, but because it's only from one realization, but whether it is consistent or marginally consistent, it's zero in the sense.
I mean, it may be partly that the color scale it enhances the effect. I mean, I can't tell because it's an arbitrary. I mean, red and blue mean whatever they mean, right? But just looking at it,
we do have it. I mean, we have it labeled in terms of the density. If you'd like, I can do a share screen if we want to look at that plot again.
No, but I'm just saying if you slightly change the color scale, maybe it wouldn't look as dramatic. But to me, when I look at that, it just makes my spidey sense go off because it does not look like a quadrupole, right? The bluest region and the reddest region are not opposite each other at all.
Right.
And I see structure in it. So it's not that I think there's also a quadrupole. It's that I think there's structure in that density field that I think is probably due to systematics, and that part of that structure you're interpreting as the dipole, but the other stuff isn't much weaker and shouldn't be there if it's a pure dipole signal. So there's probably something to be explained.
Right. So I would not say I would not argue that what we're seeing is a pure dipole. As for the nature of the additional structure that we see in the map, I don't know. We looked for correlations with systematic directions, and we looked for correlations with things like extinction.
But it's really caused by something that isn't the physics that you think that the dipole might be. It's caused by some systematic thing, because there's a couple of kind of stripes in there, right?
Well, the only thing, again, the only thing I can state with any confidence is that of all the systematics we could think of, none of them checked out. So we kind of ruled everything else out that we could. And by itself, the result, I would tend to be a little bit more cautious than I perhaps seem, were it not for the fact that the result confirmed an independent result from radio catalogs. And that's what I think, that's when we decided to really publish that this was a publishable result, was that, you know, these are survey-wise totally independent and sample-wise almost completely independent.
No, I mean, I'm not.
So in other words,
I'm not criticizing that you did the project. It's a good project to do. I'm a little dubious about the results because it doesn't look as clean as you would like it to look.
Well, no, I mean, I don't think anything necessarily does, but we are absolutely open to any and all suggestions for you know, improvement or what things to look at, and we do have our sample and all of the code used to analyze.
Following, there was a discussion earlier with George Smoot and other people involved, arguing about why people don't make all their stuff public. So I do appreciate that you guys did just stick it all on GitHub.
I really do mean
so that is cool.
The last slide, which is that please look at this and see if there's anything that sticks out, because we're all ears, because we're starting to, you know, starting to run out of ideas here for what sort of systematic or sort of subtlety could be at play.
Okay, so I think we now went through all the questions.
Sorry, Hungmil, I had one question. Sorry, I raised hand. Okay. Sorry. To Nathan, actually, so I took a look at your paper, and then when you estimated the clustering signal, I noticed that you used a bias of 1 for quasar. Did you have particular reason to choose that low bias value?
My understanding was that that was considered somewhat typical, but that is a question for Ramiz, who did the estimate of the clustering.
I think, I mean, if I understand correctly, bias of 1 means that your assumption is that quasar field faithfully trace the matter field. But I remember that for quasars in particular, with low number density and their rarity, bias value is typically very high.
So yeah, we did look at a few different bias values now that I remember. I think we went up to 3 or 4 or something. And the result was still that the clustering dipole was essentially negligible.
But it may not be as small as you estimate, right? But it's bias square. So if it's 3, then you boost your signal by a factor of 10 for the estimate.
Yeah, and I think that would be then, we'd be a factor of a clustering dipole that's like a factor of 7 less than what we see. So yeah, I mean, I would not argue that some of the dipole we see could be attributed to clustering, but we'd have to have it essentially to get within the CMB expectation.
Okay. And then what's your method to make sure that your samples are uniform over the full sky? How did you check that?
We looked at, we bin the data along preferred directions like ecliptic latitude, declination, supergalactic latitude, galactic latitude, that sort of thing, to ensure that there's no systematic trends with any sort of preferred direction. And then we also looked to ensure that the sample, that the sky pixels were following the Poissonian expectation, modulo any effect from the dipole signal. So that was essentially how we got down to the confidence that if there is any further systematic, it's not along any known preferred direction or with any particular region of the sky.
Okay, thanks. Sorry about the late time question.
Okay.
That's fine.
So this is not only the quasar, but a lot of these objects are AGN. Is it correct?
Yeah. So right. So the term quasar I've been using as sort of a shorthand for a mid-infrared AGN. So mid-infrared AGNs are dominant over their host galaxies typically, at least for the color cut that we've used. As an AGN person, I generally call something a quasar when it's bolometrically at least half as luminous as its host galaxy. And so mid-infrared AGNs tend to be quasars predominantly.
All right. Okay. Okay. Thank you very much. I think we can now close and have lunch and come back in the afternoon. Thanks to all the speakers. Yes.
Yeah. Thanks, everybody.
Thanks for the discussion.
Yeah.
Thanks.
Yeah.